Okay, in this video, we take a look at how we might develop the equation of motion for a skydiver using Newton's second law of motion. Before we begin, I want to take a quick little video from Discovery Education and show you what's happening to the skydiver as they fall through the air. So let's take a quick look at a short video. We're only going to show about 20 seconds or so of this. And so what you're seeing here is that as the skydiver is falling, the pull of the Earth is certainly speeding them up initially at 9.8 meters per second. But as the force of air resistance grows, as they go faster and faster, eventually the acceleration is decreasing to the point where they stop accelerating altogether. That occurs for this diver at around 55 meters per second. That speed there would be called the terminal velocity, and that's as fast as they can go when they stop accelerating. So what I want to do is I want to show you how we might develop the equation of motion for that skydiver using Newton's second law. Now, the textbook that you have describes how to calculate the terminal velocity for an object going through a fluid such that the drag force is proportional to the velocity. That's for slow speeds. But when we're dealing with a skydiver, the speeds are so much greater that we need to use the drag force is proportional to the square of the velocity, and that becomes a little bit more complicated, and that's what this video is for. So let's go ahead and start this by considering the very simple case. And again, your book sort of describes this, but I want to go through the mathematics here so that you see just how we might use Newton's second law and some integral calculus to develop this equation. And then we'll go through, and in the second half of this video, consider what happens when the drag force is proportional to the square of the velocity. So let's start here. Newton's second law just says that the acceleration is in proportion to the net force acting on an object in inverse proportion to the mass. In this case here, I have two forces acting. I have a weight force that's acting down and a drag force that's acting upward. Let's subtract those like this. And let's go ahead and now divide that m through, and we get g minus b over m times v. Now, since I have a variable force there, I have a variable acceleration, I have to use calculus to develop that velocity as a function of time. So a is dv dt, and let's go ahead and just write that as that. Now I have a velocity on the right and a dv on the left, so I'm going to go ahead and collect those terms. And let's bring that dt over to the other side. And now I'm pretty close to a point where I can start to integrate. I'm going to pull out an integration table to see what it looks like. It looks like I have a dv over a v value, and that's very much like a natural log function. So I'm going to go ahead and clean that up a little bit so that I can do integration fairly simply. I'm going to start this by just multiplying both the numerator and the denominator by a negative m over b, and that's just to give me a v in the denominator with a coefficient of 1 instead of a negative b over m. Again, there's multiple ways to do this math, but I choose to do it this way. So now what I'd have is a negative m over b times dv all over v minus mg over b. And I might even bring that negative m over b to the other side and get it something like this. Okay, so just a little bit of math there. Now I'm in a position where I can go ahead and integrate this. So I'm going to integrate this, both sides. This one's going to be from 0 to v. This one's going to be from 0 to t. And took some time to get this to a form that's easily integratable. And so that would just be natural log of v minus m g over b. And I'm going to evaluate that from 0 to v. And this one here, very simple integration. Don't need a table for that. And that looks good. Let's go ahead and plug in the value for v there. And then subtract where I put in a 0 for v. Okay, and on the right-hand side, when I plug in the 0 for t, I get 0, and that's all I get on the right-hand side. I have a difference of natural logs, so let's go ahead and combine those with a fraction. So Okay, and there we go. To clean up the left-hand side, I'm just going to go ahead and do this here. And I do that by taking this and having that be to the exponent of the natural log e. So that, that e to the negative b over m times t allows us to clean that up nicely like that. Let's go ahead and multiply both sides by the negative mg over b. So we get this. Let's bring the negative mg over b to the other side. And since I have a common factor of mg over b, let's go ahead and just factor that out to make it as simple as possible. And there we go. Our equation for the velocity is a function of time for an object falling through a fluid in which the drag force is proportional to the velocity. Let's just evaluate this really quickly. When t is equal to 0, this term here would be 1. 1 minus 1 is 0, and I get an initial velocity of 0, as I expect. As t becomes really big, this term here is going to start to approach 0. So now I would get a terminal velocity of mg over b, and let's see if that makes sense. Terminal velocity, when these two are equal to each other, then the velocity would be mg over b, and that's exactly what this equation is showing. So I like it. That's the terminal velocity as a, or rather the velocity as a function of time for an object experiencing a drag force that is proportional to the velocity. Now, I want to take this back to Desmos for just 1 second and just see what that graph looks like. So I have that equation already written in here. Y, which is for me my velocity, mg over b times 1 minus e to the negative b over m, and my t value is going to be x. I need to put in a value for b. Now, when I look up drag coefficients for skydivers, most resources say that the drag coefficient is maybe 0.3, maybe 0.2 to 0.4, somewhere in that area. Let's go ahead and just try to put that in there and see what happens. Put in a 0.3, and sure, I get that characteristic shape of that graph, but you notice with that drag force or that drag coefficient being 0.3, which is what the internet is telling me that value is, they would have a terminal velocity of, looks around 2450 meters per second. That's what, 3.5 times the speed of sound. So that's certainly not the case. I could try to put in a much higher drag coefficient. Let's put this down to maybe 14 or something and see what that looks like. But we're sort of definitely outside of the speed range in which the velocity, the drag force would be proportional to the velocity. So I think this is just not a good model for it. So what I want to do now is I want to take this and show you how we might do the similar mathematics, but dealing with the drag force being proportional to the square of the velocity. So we're going to start it the exact same way that we did before. Acceleration from Newton's second law. The only difference here is that now I have a bv squared term like that, and when I go to reduce that, I get g minus b over m v squared. Okay, so just like I did before, I said dv dt is equal to g minus b over m v squared, and I just sort of bring this over to the other side. I'm going to pull out that integration table now and see if we have something that's similar to that. We have dv over some sort of v squared term in there, and I see I have some dx's over x squareds over here, and I have plus a squared or minus a squared, and I have some different integrations there. So I'm going to go ahead and try to clean that up a little bit and see which of these things it's most similar to. So let's start by cleaning up that v squared, have it be a coefficient of 1. And so I'm going to multiply again by a negative m over b over a negative m over b, and that allows us to make that be a v squared coefficient of 1 denominator. So let's see, this would be negative m over b dv all over v squared minus negative mg over b. And I shouldn't say negative. There we go. Looks like so. And that all looks good. Is equal to dt. And I'm going to bring that negative m over b to the other side. And I like it. I have an x squared minus a squared, v squared minus that. So if I consider a squared to be mg over b, and I let that x squared be my v squared, it looks like it's going to be this one here. Now I do have to evaluate, do I have x squared greater than a squared or x squared less than a squared? Because the integration is different there. So let's see if we can figure that one out. According to this up here, I'm assuming mg is bigger than negative bv squared, right? Because it's accelerating downward. So let's just see what that looks like. We're saying that bv squared is less than mg while this thing is speeding up. So v squared is less than mg over b. And if I look at this, if this is my x squared term and this is my a squared term, what we're seeing is that it looks like we have x squared is less than a squared. Okay, yes, that looks right. So according to that, if x squared is less than a squared, it's the bottom one here. So it's negative 1 over 2a natural log of a plus x over a minus x. So there we go. Let's go ahead and use that. So let's go ahead and do this integration now from 0 to v and do this integration from 0 to t. Okay, so here we have negative 1 over 2a times the natural log of a plus x all over a minus x. And thankfully I have that from the integration table. I'm going to be evaluating that from 0 to v. And on the right-hand side, I just have that negative b over m times t evaluated from 0 to t. So there we go. Let's go ahead and plug in a v for the x and then a 0 for the x and just clean this up a little bit. So negative 1 over 2a natural log of a plus v all over a minus v minus negative 1 over 2a natural log, see, a plus 0 all over a minus 0. Well, that's nice. That's the natural log of 1. The natural log of 1 is 0, so this entire term just goes away. And so that's nice. That cleans it up a little bit. It's equal to a negative b over m times t. Of course, when I put in that 0 there, that term goes away, and I just have that. And so there we go. I like it. Let's take this thing up to the very top now. Give us a little bit more space and see if we can't start to clean this up a little bit more. So first thing I'm going to do is I'm going to take the negative 1 over 2a and bring it to the other side. So I've got a natural log of a plus v all over a minus v, and that's equal to, let's see, a negative 2a times a negative b over m times t. And there we go. Let's go ahead and just make this be equal to 2abt over m. There we go. All right, so just like I did before, I'm going to take this and have this be e to that power so I can get rid of that natural log on the left-hand side. And let's go ahead and multiply both sides here by a minus v. And we get a plus v is equal to a minus v times e. So that power. And now I need to bring that v over to the other side. So a little bit of algebra here. Hopefully I don't make a mistake with all that algebra. Okay, bring this one over here, and I get v plus v. Bring the a over here to the other side. and then minus a. Getting close. And just one last step, I'm going to bring this over here. So I have velocity is equal to a times e to the 2abt over m minus 1 all over 1 plus e to the 2abt over m. Okay, and we're really close now. I just need to do one last step where I replace a with the square root of mg over b. Okay, and it's going to make it look sort of ugly, but I think we can do that. The square root of mg over b times e to, let's see, square root of mg over b. I have a b there, I have a t there, and I have a 1 over m. So I'm just going to write it out linearly like that, if you will. Don't forget that minus 1 down here. And then down here, thankfully, I have the same exponent. There we go. Now, to clean that up, velocity is a function of time. Square root of mg over b times e to the second power. I've got a t there. Now, everything else, I have an mg and a b, and those are underneath the radical, and I have a b and an m outside of there. So I'm just going to use those exponent rules. The m's to the 1/2 power, that's to the -1 power. So when I put that underneath my radical, that's going to be a m in the denominator. Now I have a g in there. That g is going to stay in the numerator because there's no g's out there. I have a b to the first power, b to the -1/2 power. That becomes b to the 1/2 power. So that's underneath that radical, like so, minus 1, all divided by 1 plus e to that same power. So 2t square root of gb over m. Okay, and there is my expression for the velocity as a function of time for a skydiver, if we're assuming that the drag force is proportional to the square of the velocity. Now I want to take that and put that into Desmos and see if that graph actually closely models the actual velocity there. So let's go ahead and take that into Desmos, and let's add a new one down here. Okay, so there we go. Let's go ahead and get rid of that one for a second. With a drag coefficient closer to the 0.3, which is what the internet tells me is the drag coefficient for a skydiver, we get something that's looking pretty close there. It looks like our terminal velocity, that's about, what is that, 50 meters per second. For our skydiver, we had it closer to about 55. And so, yeah, I could put that in as a drag coefficient of 0.27. That looks pretty darn close. There's 50, 55 is maybe a little bit higher. Close enough. I would say that's pretty good. And let's take a look at the time value. It looks like it takes in the neighborhood of 5, 10, 15, maybe 15-ish or so seconds for that person to get up to that speed. And if I come back here and look, that they started around 8 seconds there, and they got to that terminal velocity at around maybe 22, 23. So it's about 15 seconds as we expected. So I would say that this equation there correctly describes the velocity as the function of time for a skydiver. Of course, you could always change this up a little bit and see if they're a little bit heavier. 85 have a little bit higher terminal velocity. That's getting up there a little bit more. So instead of 55, maybe 58 or so meters per second. And if we were to put in a drag coefficient that's greatly increased when I have the parachute open. Let's put that in. I don't really know how big that drag coefficient would be there, but we could certainly model that. The terminal velocity once our parachute is open is closer to about 5 meters per second. And so let's just go ahead and keep adding these things in here. That drag coefficient, when I get that parachute in there, yeah, that's getting a little bit better. So we can certainly see that. So it looks like this equation is the equation that we would use to describe the velocity as a function of time, assuming drag force is proportional to the square of the velocity. And that completes the video.